Hello everyone. Now we are doing the third part of this lab, which is deep reinforcement learning. We will be using a library called Keras-Rl. It is not an official library. It was created by a researcher who used to work with TensorFlow 1. Then he or she, I honestly don't know, did another version of this to work with TensorFlow 2, and it was called Keras-RL2. The example I'm showing here is not my own. I downloaded the file from this link. This is the GitHub repo for Keras-RL2, and it has a subdirectory called um, examples, which has many examples there. Okay, so when we start, we will import NumPy, import few things from TensorFlow, Keras, and so on. It usually should be imported this way. I'm not sure if we can use the same imports that we used in the previous file, um, mainly because there are some low-level optimization that's happening within Keras-RL2. So I prefer to use it the same way it was listed in the example here. Usually use PyTorch for reinforcement learning because it's more flexible in terms of designing the networks for actors and critics. But Keras-RL2 is the best one to for educational purposes, in my opinion. Okay, so there is, we'll import from RL. This is the library that was installed. rl.agents will import DTPG agent. DTPG stands for Deep Deterministic Policy Gradient. And the reason I'm going with this one because we will show some of the classic control problems and how they are being solved with deep reinforcement learning. DTPG is considered one of the best when dealing with classical control problems. The second one would be we'll import from memory, we'll import a sequential memory. The memory concept in of policy deep reinforcement learning agents is basically a way to store samples that we will train on. Remember when we talked about the different ways of incorporating neural networks, it can either if, approximate the Q value, or it can approximate or give us a decision which action we should take. But in both cases, there is a table of all the data that's been collected, and this is where this table is stored. Finally, there is from random, we'll import Ornstein-Ohlenbach process. I'm not sure if I butchered this name enough. Basically, this is random number generator, or it uses a random number generation, but it does it in a slightly fancier way. The idea is to use it for exploration. So when the agent starts working, it doesn't know anything about the environment. It needs to explore, so it will do some random actions, and from this, it will start collecting some data to train on, and then start learning how to work through this environment. The benefit of this particular process is that it does not produce noise in the actions at the same level at the start of the episode to the end of the episode. It actually diminishes as long as you go through the episode. So the very first few steps it will be a little bit erratic, but this will saturate eventually, so the impact of the noise will be diminished by the time that the agent will actually start learning something. In my research, I usually use just Gaussian noise, random noise. It's much simpler for me to actually work with. So let's run this part. Now the second part would be importing or using the environments. This is the environments that we will be training through. Notice here when we imported gym. This is a framework designed by OpenAI, and it's basically creating different environments to as a gymnasium for the deep reinforcement learning agents to train and learn from it. And it's kind of the standard problem when publishing research. If you publish a new agent or a new training algorithm or any of these new techniques, you have to test it on all of these environments to showcase how good it did compared to other systems. So our first example here will be using the pendulum environment. So we'll just put it in a variable here. And when you have a new, when you need to use an environment, you say gym.make and give it the environment name. We'll return that into an environment variable. This environment variable is different wrappers really around the core logic of the actual environment. Again, don't forget to set the seed for the numpy and set the seed for the environment as well. Here we are checking that the action space.shape is 1, meaning it has 1 dimension. Now let's see what the environment has. If the environment has an observation space and an action space. The observation space is the inputs that go into your deep learning model, and the action space is the output actions that can influence the environment. Right now we cannot really make much sense out of these, so we need to check the documentation. And for that you go to gemlibrary.ml, and here you will have a list of all the environments. This environment pendulum in particular was in classic control, and it was this one. So our observation space, the shape is 3, and it takes it provides the limits of all the inputs that are there, which are the highs and the lows, and this is how you use this environment. Now the observation space here has 3 inputs. First one is cosine theta, second one is sine theta, the angle, and third one is the angular velocity. I would like to emphasize here how good this is. Now let me show you something. This is the example. You have this rod, it's falling down by gravity, and the agent is supposed to learn how much torque it should apply left and right to keep it standing upright. The neural network model is usually, or is by definition, a linear regression, so it is a linear system. If you're feeding it values that are nonlinear, it will work eventually, but it will take a lot of time to come to terms with that. Here what they are doing is actually linearizing the input. This is part of the pre-processing of the data, as you did before and as you're doing now in assignment 2. You can modify the data any way you want, modify the inputs or the outputs any way you want, and you always do that to make it more digestible to the machine learning model. So using these cosine and sine mainly makes the measurements linear instead of being non-linear. Wish I can say the same with angular velocity, but I think it's already linear because it's on the tangent of the circle anyway. So yeah, this is our observation space. We take 3 values, and this is our action space. It produces 1 action, which is a torque, and the minimum is -2, maximum is 2. Now we take this information and we'll get the number of actions equals the environment action space dot shape sub 0, which is 1, and then we'll start building our actor and critic. Okay, our actor is a sequential model. We'll add a flatten, mainly just in case we are inputting an image or anything in other environments. So I will show you some other environments like Atari. The inputs or the observation space of these environments will be an image. Observation would be an image, and each one of them will be from 0 to 255 or something like that. And the actions will be something like this. So the idea of the flatten here is just to make sure that everything will be flat, because well the model here is using all dense layers. Okay, we'll put our input shape equals 1 and plus the environment of action space shape. Now I want to show you how this works. Copy that, paste it here. This ends up 1 and 3, which means that we have 3 inputs and we reshape them into a row vector 1 by 3. Now this would be the input going in. This will go into a dense layer. You put an activation, tanh, sigmoid, pick your poison here, doesn't really matter. It matters, but not in the greater scheme of things. And then you can still add few more layers and some activations here and there, and eventually at the very end this would be our action. This produces number of actions. Number of actions is we copied from the environment action space shape sub-0. Now this action will be then passed through an activation. In this case it was sigmoid. We will talk about this because we might change this. This is not supposed to be working this way. And then we'll multiply this by 2. We'll talk about these two for now. Okay, so this is our action. This is the activation function that these actions will be mapped through. We need to check again what is the action, what's expected from the agent in terms of action. It is a torque and it is from -2 to 2, so we have a negative component. And sigmoid maps from 0 to 1, so we need to change this to tanh to map it from -1 to 1. And one more thing here, we have -2, so we need to multiply this by 2. Now we can add a custom layer. It's called the lambda layer, and basically what it does, you define an anonymous function here in between, and whatever comes into this variable will be multiplied by 2. So basically what we're saying is get the actions, whatever actions will come out of these dense layers. We'll pass it through tanh, we'll make sure it's between -1 and 1, and we'll multiply it by 2, so it'll become between -2 and 2. And this will be our actor. We'll print the summary, and there you have it. This is our actor here. Fairly, relatively big one. Now we have 2.2k parameters to optimize. And that's only one half of the story. Now let's make the critic. Now remember, the critic has to take the actions and the observation into account. We have the slides here, and so we have our actor here. The critic will have the action and the states, the observation, and we need to concatenate both of them here. So We'll start with what the action input is. This would be an input layer which with shape number of actions, and we'll give it a name here. Now we have an observation input, another input layer of one, and observation space dot shape, same thing we did here, and we'll call it observation input. Now we'll flatten the observation just in case it was an image, and then we will make a concatenate layer which takes action input and flattened observation, and we'll return all of this into X. This method of creating models, we could have done it the same way here, but in this way of making the models, mainly returning the last layer that was created, and then next time you add a dense layer, you pass the last layer, and it will keep stacking layers on top of each other. The reason we're doing concatenate this way, this basically creates a new layer, and this layer, it takes an argument inside of it, which is that part. It's like a function calling a function. And same way is done here, 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 and there. Now the last layers in the critic are basically one value, because this is our Q value here. This is what we're trying to do. And the activation for this one should be linear, because we have no idea what the value or what kind of reward this environment is providing. Is it negative? Is it positive? We don't really know. So we should not really map it to anything, so we'll keep it linear at all times. Now, all of these are just group of layers stacked on top of each other, and that's it. There is no model yet. So we'll create a model, we'll call it critic, and we'll define what the inputs are, which are action input and observation input, what the outputs are, which is this stack of layers there. And then eventually we will print that. We'll run this, and we'll see this is our critic. By now you start to realize that you are diving deeper now into the rabbit hole, and models will get more and more sophisticated as you start working with this type of work. Naming the layers will be critical, of utmost importance really, because eventually you will have to debug through the layers, and you need to know which layer is producing a feature map that you don't like. Okay, now let's go into the training. We'll define a memory. This is the buffer that will hold the data that we will train on. Sequential memory will give it a limit of 100,000 and a window length of 1, meaning it will, when it chooses a sample, it will take just one sample. It does not take history into account, so it does not take this sample and the one before and the one before. If this was 3, then I will be taking 3 samples consecutively at a time. And the random process here we'll do using Ornstein-Uhlenbeck process. And again, these are the parameters just for the mean and variance of the process. Feel free to look into this. It's already, if you type this, if you copy that one, the whole thing actually, and put it on Wikipedia, you will find a very informative piece on it. And now we are ready to define our agent. Now our agent is a DDBG agent, deep deterministic policy gradient. We'll take number of actions equals MB actions. We'll take the actor network and the critic network. We have the critic and action input is action input, which is, where's the action input? There it is. We'll give it the memory that we defined up there. Now there are warm-up steps. These are just steps throughout the environment that the agent can just collect data and does not train the network. The reason being, we don't really want to train the network on rubbish data. So if it's exploring extremely random at the start of the episode, then um, we need to collect this data without training the network. So it disables the training for the first 100 steps here. Now, the random process is the random process we defined up there. These two variables, the gamma and the target model updates, are quite interesting. As you might have noticed, the network we're training on here is training on the table of the data that we collected. And when we do that, next time we will be sampling more information or uh, more inputs or more observations from the environment. And now, whatever actions you did here, some of them are good, some of them are bad. Eventually, you will find new situations that will be added again to the dataset. So the dataset is not finite. And when you're training this way, the network will be, the gradients will be kind of erratic. So it will go one way in few steps, and then will go completely the opposite way in few other steps. And training the neural network this way is not really efficient. It's not even guaranteed that it will converge this way. So what they do is that they have another copy of the network. We'll call it the target network, and this network will be used to um, predict the actions and train on it. And this network will be used to as a storage. So we'll get these weights from this network, copy it to that network, and then keep training on that one, and then copy again to that network, and so on and so forth. This is called the target network, and this is called the direct network or something. Now, the weight that you would be using when using the new network, so if we have net 1 and we have net 2, uh, let's call this target, and this would be source. So what we want is net target equals the target model update times net source plus 1 minus the target model update times the itself. So it's basically a weighting factor to decide how much information of the new network I will keep in the storage of the target network. The gamma here is the discount factor that we used in, where was that equation? Mm, there. Awesome. The next step would be compiling our model with Adam learning rate, whatever. Clip norm here is mainly to make sure that the gradients never go above 1. These are like the tips and tricks that you're gonna have to deal with when you're working with reinforcement learning, because you cannot know what the agent will face and what kind of crazy actions it will do and how that would impact the environment, and how this impact will actually reflect back on the training. So sometimes we usually have to clip the gradients there. Okay, so we'll run this one. And now we're ready for the training. We'll pass the environment, which we defined upstairs, and then we have number of steps, 50,000, whatever. Visualize mainly to just show you how things are going. The graphics part. Variables here is for reporting, and maximum episode steps. This is mainly, it says I will try this environment for 200 steps. If I don't solve it in 200 steps, then I will start again. The idea here is that if you go into a bad state you cannot recover from, there is no point of actually staying there forever. After you train your model, you can save the weights, and then you can test your model on the same environment, and you can also change number of steps per episode and so on. So let's run the model, and this should start visualizing here. Now you can see here it is trying to push all the way to the left, push all the way to the right, and we'll keep training there. I want to show you a few things on how the reporting is doing. So there is a deprecation warning here because the library is fairly old. Okay, what's happening here is that it is sampling data from the memory, and every time it actually acts anything inside the environment, it is updating the memory with new observations. And from this, it tries to update the actor and the critic, and it is then every few iterations it will start copying this the weights from the new network to the target network. This I believe this is doing 50 episodes each. Let me see. It's not specified here, but I believe it was 50 episodes each. So by the time this will finish to the very end, it should say 50 or 100 episodes have been examined. By now the agent is experimenting with the limits of the torque, and I think it's now figuring out that it has to maybe take it slow on one direction and then push hard on the other direction to keep the momentum. Deep reinforcement learning methods of algorithms take very long time to train. The models I showed in the videos are um, they took actually days or sometimes weeks to learn, and yeah, it it is something that we'll have to deal with in terms of reinforcement learning. DeepRL as well is considered now the way to have artificial general intelligence. It is being used in some optimization problems, and it is being used in some of the problems associated with self-driving cars. Not all of them. I think it's mainly for data preparation. It's still too dangerous to let the agent drive the vehicle on its own. Now the agent started to realize that it has to keep flipping between left and right to maintain this. Um, Now it is pushing left and right to get the momentum and trying to stabilize. The larger this arc is, the larger the torque was in terms of the action. If the action, the activation function of the action was left as sigmoid here, then it will be going only in one direction, which is because it has the values mapped from 0 to 1, not from -1 to 1. I'll speed up through these episodes and then upload the final file. There are also other examples, so maybe let's copy this one, and then if you check the examples here, oh yep, by the way, you can follow the installation guide here to make it work on your machine. And if you check the examples here, I think I should take this here just to keep an eye on the trading. Now, so there is DDPG for pendulum, there is one for the carved board problem, there's also DQN for Atari, and so on. So you can download any one of these and start working with. It will give you like a backbone of the algorithm, and then you can uh, tweak it and tune it to your liking. Now it finished the first 50 episodes, and it's reporting now the episode load. I think this is an average, this is a minimum maximum, and then the overall loss and the MEA, the mean absolute error. And I believe we actually asked for the mean absolute error here in the matrix when we're compiling. And also the mean Q value that you get from um, the critic network. You can notice now it started to actually slow down once it reaches the top and it's trying to actually balance things here now. This is not the final solution yet, it's just on its way, but it's good to see it actually learning how to do things. Now the second interval, which is the second 50 episodes, it will it should have a higher episode reward, and this is the live reward being changing, and you can see it dropping once it is actually stabilizing there. Now if you want to check other environments, I would recommend for the classical control to check the card pole one. This is a discrete action space, so you can it mainly says move left, move right, and it's trying to balance the about on top. The observation space here is the position velocity of the cart and the pole angle and the angular velocity for that. The action space is just move left, move right, and so on. Another one I really like is the box 2D environments. It has the lunar lander. This is a nice environment there. Mainly you are trying to land this spacecraft on in at this launch pad. It has two versions. One of them is discrete action space, which is this one. It has either do nothing, fire left, fire main engine, or fire right orientation engine. So basically, you're either slowing down by firing the main engine, or you fire on left or right to actually steer the spacecraft there. There is also a car racing example, and this is a continuous action space, but the observation space is an image, so you will need to change um, you will need to change the input of the actor of the observation here into um, you can either use it like this and use flatten, or you can have a convolution on your network here. There was one more. Bipedal walker is mainly this two-legged robot is trying to run through this terrain, and this has an action space, a continuous action space, mainly motor speed values for each joint here. You have two knees and two hips you need to operate. The observation space is the orientation of the object. I think the also the joint angles happening, and there is a tiny little laser here that is scanning the environment for you. I think now the agent started to learn how to balance the road upright, so it is doing really well. Now the average view episode reward now has dropped significantly from the first 50 episodes to the second ones, and we've even started to see rewards that are closer to zero. So the reward here is mainly a cost function. In this particular problem, it is a cost function. It cannot go above 1, so above 0. So it is mainly just measuring the distance between this being perfectly upright, which is 0, and then the cost associated with being tilted left and right. There are other environments as well. Some of them are toy text based, like blackjack or taxi or something like this. There are Atari games here, heaps of Atari games, really, many of them. And I believe there was a bipedal. The mountain car here is you have this car. The idea is that the agent will have to go all the way up and use the gravity and then push all the way here until it reaches there. There was another problem. The Mojoko ones, the Mojoko environments. This is the one that Google and DeepMind used when showcasing the agent that learned to walk. This requires a special library to be installed, and it has a free trial, but there is a license that you have to apply through. This is the example I'm talking about, humanoid learning to stand up. There are also 3 third-party environments, and there are heaps of those. Uh, the ones I showed you in my slides before is called OpenSimRL, and this is um, basically this is driven by OpenSim. OpenSim is a software for biomechanics simulation. It's made by Stanford, and they made this environment for reinforcement learning agents to start teaching agents how to walk and run and so on. Every actuation here in this environment is driven by muscle activation. So there are no, you don't specify joint or a motor angle. You have to actually operate the muscles and deal with what the muscles are causing. Another one was the biomechanics simulation for the eyes. This one is not published yet. It is released on GitHub. It's done by one of my PhD students, and but I don't have the link handy here. I will keep it in link it in the description. So up to the third interval now. We're almost done. I think we will terminate the process after we finish this iteration. Reason I just want to say what the episode reward, the average episode reward would be. I can see here that it is actually very stable in balancing this one upright. One of the things you start noticing is that it sometimes flickers here, which means it's oscillating between left and right, and this is one of the things that you might need to consider when you're working with this kind of models, is how applicable it is. Is this something that can increase the wear and tear on the joints in your system, or is it something that is acceptable to be done this way? Is there a way to smooth things up? It's going crazy here right now. Is there a way to smooth these torques and make the system more stable? We can see here the agent is really going crazy trying to balance this one, and it's going left and right all the time. One of the examples I didn't get to show you is learning to stand here. This is based on the OpenSim environment, but what we did here is actually we learned multiple policies, and each policy has their action, and then we learned another policy, coordination policy, that can choose which one of these policies to actually work with. This could be a discrete choice, so you can say we'll go to policy 1 or policy 2, or it can be a weighted average between all these policies. We have also a similar one here um, with the eye movement, and this is a more articulate one. So in this one, we're just choosing blindly what policy to choose. In this one, we are the 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 way the actor is designed is following the same way the different parts of the brain are being interacting together to actually get all the muscles coordinated properly. And there is a separate module here for a more interactive sigmoid, and which is similar to the tanch one that we have done here. Basically, if this is your function, the activation function, tanch ka minus k uh, a0, then we need to approximate what the k is, what the a0 is. So we'll make a neural network here to estimate the k, make a neural network here to estimate the a0, and from that you can get the agent to learn different shapes of tanch. So these are different shapes of the tanch function, and it uses each one of these shapes depending on what the environment is feeding it. So it's part of what the observations propagate, how the observation propagated through different layers and then reach this layer that splits to estimate the k and the a naught. This is the one that we have showed here. The idea here is that you'll see in the proposal it's a little bit more stable, and this is translated in reaching the point faster. The one at the top is almost fell down a couple of times, and so in trying to balance this, it took some time. Another thing is to keep an eye on the actual body here. You will see the body at the top is actually oscillating up and down, and the body at the bottom is fairly much more stable than that. This is all translated into more effort and more work been done to actually balance itself at the top, as opposed to the proposed one at the bottom, which allowed it to reach the point, the final line faster. I think now the model should have been trained enough to actually be good. Oh yeah, look at that. Episode reward now. The average is minus 145, and we actually, in many cases, in some cases, we reached the almost zero one. I have other examples like this. I'll show you one here. This is the lunar landing one. you can see that the post one goes reaches faster than this is obviously sped up, and the reason it's reaching faster is that it is actually making use of the free fall and then saving at the very last minute and then steer itself, while the gray one will try to slow itself down at the top and wasting more energy in doing this. This is the same example we showed before. You can see here that the steps are not really, the steps are sometimes it takes double steps with the same leg because it was almost falling, and this is, in this case, the steps actually took some extra steps in the air, and yeah, so all of this is wasted energy and wasted effort there. This one should really talk about. Now this back and forth oscillation on the in the classic model is mainly translated into something like this. Well, I'm not really an electronic or electrical engineer, but I think this kind of oscillation might be a problem somehow. It is kind of unstable the way I see it. The On the proposed method, you can see here this is a very smooth response in terms of the actions transmitted here, and it's reaching the same one. Alright, I will stop here. I think this is a safe point to stop. Have a play with different environment, different variables, and then try different models, bigger, smaller, and so on. These kind of environments, especially if you're using all dense layers like this, you don't really need a GPU for that. You can actually do this on your laptop or on your machine. Just don't go crazy with all the layers and number of neurons per layer here, because it can go can become very tedious to train. Awesome. Have fun, and again, my apologies for the inconvenience that happened last week. If you would like, as I said in my announcement, we can take special session for separate groups or even one by one. We can allocate face-to-face session. We'll do whatever it takes to get you up to speed with the material. Thank you.